Cool. Okay. Hey, everyone. So we're going to stream for the next couple hours. I'm going to talk through basically some topics I'm just interested in personally. Not anything I know about or really have much expertise in. But I thought it would be a fun way to kind of, I don't know, waste a couple hours. For whatever reason, the AI stuff's been going so hard this year. It's like all we ever talk about. So it's a good opportunity to learn something new, try out something different, or I don't know, just learn about it as we go. So I think everything's set up from my end. Let me know if there's any issues with the connection or anything like that. I think chat's working. I'll be kind of half on Twitter as well. So yeah, let me know if there's any problems. So basically what I wanted to do today was work through an area I've kind of wanted to learn about for a while, which is how WebGPU works. I haven't really spent too much time diving into this, but I think you can run some WebGPU examples in Python, and I think it's a different way of kind of using GPU on the web to do interesting things. Instead of kind of diving into AI examples, we're going to mostly focus on using this for kind of doing straight basic graphic examples. So I want to kind of first dive into how this is actually used before we talk about compute or things like that in the future. I know there's a lot of folks I talk to online and in real life who are using this to kind of run ML stuff online. Okay, so first before we get to the coding part, let's just talk about what this technology actually is and why it's interesting. So basically, it's going to allow us to run these kind of shader programs just on the web that are going to fall into the GPU. So my understanding is that there are kind of like two of these languages that people use that are pretty popular. And one of them is going to be, let's see if we get this working. Here we go. So one is the open, I got white strokes going on. Cool. So one is like the open GL shader language, GLSL, and the other is going to be basically the Microsoft version of that. And what we're going to code in today is some kind of hybrid new thing that people kind of recently created, which is going to be the WebGPU shader language here. And it's somewhere in between these two. I think my understanding is that these are all like somewhat equivalent in the power they have, but the WebGPU one is a little bit nicer. The syntax is going to look roughly like Rust. We're going to have basically just that syntactic formulation, but we're going to be able to kind of port whatever we want between these various languages in order to run them in practice. Now, in addition to this setup, there's also just different ways of running and using this WGSL language. So I think the one we're mostly going to focus on today is this thing called WGPU. So WGPU is a Rust framework that actually kind of runs the scaffolding in which we run WGSL. And in particular, we're going to look at a Python binding of this, which is called WGPU Pi. I think this is actually lowercase, like this here. So we're going to basically code using this WGPU Pi. So let's go to the website for that. So this is the core WGPU library. This is going to be basically an implementation of this WebGPU spec in Rust. And you can build lots of really interesting things in this setup. And the one that we're going to utilize on top of that is called WGPU Pi. So this is kind of a quite powerful binding on top of this Rust framework. It's going to allow us to run these basically shaders in this new programming language, and it's going to do it all through Python. Yeah, so that's basically the setup. You could also do all this through JavaScript. I think that's what's particularly interesting in practice, is actually running kind of WebGPU on the web. We're not going to get to too much of that today. That is going to look basically similar. I mean, you're going to be using exactly the same shaders, but using a slightly different framework around it. Of course, you can do the same thing in Rust as well. You compile it down to basically WebAssembly, and you can run it there. Now, it's a little less clear why you'd want to be doing this in Python. It's going to be a little harder to run things on the web with Python. But the main kind of benefit for us is going to be that we can draw really interesting things using Python itself, get interactivity, have all this stuff be really efficient. And hopefully in the future, when things like PyScript or other ways of running Python on the web get better, then we'll be able to kind of run that in practice. So this is really going to be our main focus today. So let's label these. So this is going to be Rust. This is going to be like the Python bindings on top of that. Now, one thing I've learned about this kind of graphics programming is that it's unbelievably complicated. There is just so much depth to where we can go into how this works. And I think when learning about this for the first time, I found it just a little overwhelming to really try to learn, say, 3D graphics and lighting and render pipelines all simultaneously. There are textbooks on this, but they're not the kind of thing you can kind of dive in a day and understand what's going on. So in particular, there's just like a tremendous amount of jargon that make things a bit more complex. However, there was one tool that I found extremely helpful in understanding what's going on, which is this very famous website called Shader Toy. Actually, I think I talked to some computer vision folks, and they got me excited about this to begin with. So Shader Toy is basically this website where people make these just incredible graphics programs. So here we have an example of kind of a crazy one. And what's cool about Shader Toy is any one of these you can kind of click on and dive in, and you get all the code. So maybe this is a little bit small. Let's make it a bit bigger. So basically, this code here is code in the OpenGL shader language that describes everything that's happening in this graph here. In fact, this is actually rendering the shader directly. And this is just awesome, right? Like this is, I don't know, 63 lines of code. It's unbelievably complex. There's all sorts of kind of mathematical functions going on. But the output of the shader is this thing on the left, right? So it kind of, I don't know, makes you curious what's going on, makes you want to learn about what's happening and what's inside the system itself. There are a trillion of these. A lot of them are much simpler, and they do things, I mean, they have full on, I think this one has mouse interaction, so yeah, we can zoom in and out. Oh, sorry. We can, yeah. Yeah, you get the whole description of what's going on. Now, I mean, this code is kind of way too minimized, right? Like it's pretty hard to figure out what's happening here. But there's a lot of reasons why this is an interesting kind of language to think about these days. One is that there's just not that much code in it. The other is that it gives us a great opportunity to kind of play with using language models to help us write and to understand what's going on in new systems. So the kind of goal of the stream today is to basically draw some of these from scratch and try to learn about what's happening and what's working. Now, you can do it in the website here, but I think that's a little bit less interesting. So what we're going to do instead is we're going to use basically a Python implementation of Shader Toy. So this is a library based on WGPU Pi. So that's the Python binding to the Rust implementation of WebGPU. So we're going kind of several levels deep here. And what this allows us to do is basically write WebGPU shaders in Shader Toy with just several lines of code. We can then look at them and see what they look like in practice. And it's a good excuse to learn this weird language. So I thought we could just go through a couple examples. There are some textbooks that provide some descriptions of how these work and what's going on. So we can read through some of these and try to figure them out. I've also found that language models are pretty good at this stuff, even though it's it's a relatively new language, they're able to kind of translate between languages and give us good descriptions. So I think we'll kind of iterate between coding it ourselves and just kind of asking Claude to kind of let us know what's going on. So that's the plan. Let's get started. Cool. Okay, so let me just give you a quick tour of my setup so that it makes sense on your end. I'm coding basically using an editor known as Z. I've played with this editor recently and I found it to be really helpful and particularly good at integrating in AI things. So we have up here, we have our code itself that we're working with. At the bottom, we have our terminal. And then when we need to kind of consult the AI, we can kind of pull out a menu here and have it write code or talk with us as we go. So we'll get started just by ourselves, and then as we go, we'll basically consult and ask questions. So here's the directory. We're basically starting out with pretty much an empty directory. We've installed the shader toy system, basically just using a kind of standard pip virtual M setup. I'm going to try to keep the code relatively short so that it can fit on one screen, but please feel free to ask questions if you can't see things or they fall off the screen itself. So I want to get started by first making a kind of simple directory to start with. This will be just our base shader toy starting point. So we'll call this simple.py. We're also going to make another directory, folder, a file, with our actual shader itself. So we'll call that simple.WebGPU Shader language, like that there. Great. Okay. So to get started, we're going to follow the shader toy setup. So that's this code here. Their setup for launching these is pretty basic. So we're going to basically remove this part for now. Instead say that is open of our simple.wgsl file. So this will be basically the code for creating the shader itself. This part is importing the shader toy. Here is the shader toy itself. We just tell it the code we're running and the resolution at which we want it to run. Let's make it square just for visual simplicity. And then we show it as we go. So that's basically our setup to get started. And let's go into our setup here. So now we have basically, this is going to be the code that runs the shader itself. As I said before, the examples that we're going to get in are in a slightly different language. And we want to convert them into the WebGPU Shader language. So let's maybe just ask an LLM to do this to start with and see what happens there. So what I can do is write code here just to ask it to do our conversion. So convert this to Cool. So here is the conversion it gave us. So we can kind of map each of these to its given part to understand what we're going to be doing when we kind of convert some of these shader toys over. That's our setup here. It's going to look something like this in our code base. So let's talk a bit through how each part of these work. So I can remove these for now because I don't think we need them in the Python language. And talk through each of the different types. So the main type we have is this vec setup. So we can do vec2, vec3, vec4. And each of them are kind of types. So we can have kind of just different types here. So we have float 32. So in our case here, we're giving it our coordinates. The coordinates are actually going to be a vec2, f32. And our output is going to be a vec4, f32. So let's space this out so we can look at it in a little bit more detail. So this is going to be our color. And this is going to be the input coordinates. Great. And for this language, this is going to be like that, like underscore of that form. And actually, I think we do not need this on our side, and this should already be F32. Cool. So there's a couple of things that are interesting about this language that we should look at to get started with. The first is that it has this neat property where you can basically access a property, but instead of saying just .x, you can say .xy. And that's basically going to return a vector of both of those values. So we get the x and the y value out of coordinate. That will then be a vec2. And you can do things like kind of standard broadcasted operations over these vectors, where you apply this division to both of them simultaneously. So what's going on here is that this is going to return a vec2 called uv that will be the normalized position on the screen of those values. Cool. So I think the rest of this should run. Let's give it a try. I think this has a slightly different name. One sec, let me look at my cheat sheet just to make sure I know what it is. I think the name should be shader main. We have the kind of Rust syntax for the function and the return. This part looks good. iResolution, let's say .xy here too. This part looks good. Cool. So otherwise, the language model did a pretty good job of pulling it together. So one other thing to note is that this let call here, this is going to be a vec3. We can say that explicitly, I believe, by saying vec3 F32. And you can see that we're able to construct a vec4 that's going to be the color we return from this function by simply passing a vec3 as the first argument and then one value as the final argument. So it's playing some games in order to make that work out and produce the full value for the final color. So we have that all together now, and we can actually run it. So let's run our PySimple. And here we go. So we have this color in the output, and it kind of changes over time. So let's look a bit more into the code itself and try to understand what's going on here. This is basically the beginner example that Shader Toy provides us. Cool. So we can simplify this a bit. So let's take away this .xy and .xy here. Since this is vec2 and this is vec2, they divide by themselves to give us our final output. Again, let's make this explicit so we can understand what it looks like. So this is basically saying that this value here represents the normalized coordinate within the frame. So it's going to be two values between 0 and 1 representing the position you're at. To give you a sense of what this function is going to do, it's basically taking a coordinate of our final output and returning the color that we want to fill in on that coordinate. So basically every pixel of our final output runs this function in parallel, and every part of the function basically computes the color that it wants to return. This line here is going to actually produce the color. Let's make that more explicit. And the color it produces is 0.5, so it starts basically fully in the middle, plus this term here. So if we comment out this final part, we'll basically just have our GB value of 0.5 or 128 at every pixel. So it'll look something like this. Oops. Let's make that more explicit. So let's say it's vec3 F32 0.5, 0.5, 0.5. Let's see. Color. What did I do wrong? Divide can't work. I see that we failed this up here, so this must be XY. Cool. Okay, so we get this gray color here that doesn't change over time at all. If we instead put in cosine of I time, this should give us a value that changes every pixel simultaneously. Cool. Okay, so we get something that basically moves between 0 and 1 following a cosine kind of pattern over time. So it gets a little bit more interesting when we actually make the pixel value determine how this changes. So that's what this line does. So this says we actually take into account the normalized x, y, x value. So this is basically a vec3 where the r and the b coordinates are influenced by the x position of uv, and the g coordinate is influenced by y. So that's this notation is like take this vec2 and then turn it into a vec3 of positions x, y, x. So let's run that. Okay, so now we get kind of influenced by the original position on the screen. We have the pixels change in that way. Okay, the last change we'll make is we'll add back this line here. This basically is just going to offset each of those values by a different constant. So basically a bias for the red, green, and blue positions along the cosine axis. So this will give us back our full original setup. Cool. Yeah, and this one is pretty neat for kind of very few lines of code. Cool. Okay, so I have some questions up. Hey everyone. Hey Sirhan. Hey Mazde. Yeah, you can see it's U, V, Y, X, Y, X in that setup. Great. Okay, so that's our first example. From here, we're going to try to build some more complex outputs. We'll run through a couple examples to get started with, and then we'll look at some of them from Shader Toy itself. So the next thing I'm going to do is to try to draw shapes using this shader language. So to do this, we need some way of kind of knowing where the pixels are in the screen. And based on kind of their values, we can set them to be whatever color we'd like them to be. So to do this, we'll write a function for the first time. So we're going to basically write an indicator function for, let's see, how about a square? We can write this ourselves, but let's first let the LLM take a shot to give us this function. So let's say write a function that returns 1 if you are within a square with boundaries -1 to 1 in the x and y axis. Okay, so it gave us just an if statement checking for the positions here. So we have our original coordinates, which are kind of normalized between 0 and 1. This function is basically giving us a square within -1 to 1. So let's expand them out before we pass them over. So we'll basically expand from 0, 1 to well, let's say like a 2, 2 to start with. So 2 times UV. Let's do 4 times UV minus 2. Cool. And then we'll just return whatever the color gave us as, say, the red of our RGB value. So basically, we've expanded the coordinates. We call this indicator function with our expanded coordinates, and then we set that to be our red value. If you're within that area, you'll be red. Otherwise, you will be white. Okay, great. So now we have a square. The way that they produced our square is pretty complex. We should be able to just do this mathematically in a simpler manner. Let's give it instructions to try to do that, or else we'll kind of cheat and do it ourselves. Yeah, I guess that roughly works. We'll start with that for now. I'm not sure if how it handles booleans though. So okay, great. Cool. So now we have a square in our little expanded world. Yeah, I have a question. The editor I'm using is called Zed. Hopefully you can see it on the screen. Let me know if you're not able to. As I mentioned earlier, the main benefits of this editor, or one of the reasons why I like it, is it lets us really easily make these queries to the language model. We can also pull up a thing on the side and ask it more explicit questions. So for instance, let's say we wanted to ask it, how is the step function defined in WGSL? And we'll say there's this function called step. It's basically going to return 0, 1 based on these values in this setting here. So we can kind of ask these questions as we go. We're using just Claude Sonnet for the AI part of the system. Cool. Hey, Keith. Great. So just to remind everyone where we're learning about this language called WGSL. We're playing in a little environment called Python shader tools. It's basically allowing us to draw these pictures pretty quickly and look at the output as we go. The way the language works is that it is basically a kind of extremely parallelized language. It is basically going to send every pixel to this function shader main, and our job is to reply with the pixel for that color. We have a couple tools at our disposal. So one is that we have these variables like iResolution and iTime, which will basically tell us over time what the current time is as we go. So let's kind of play with that here. So right now we're basically using this indicator function to draw a square on the screen. We're passing it this expanded coordinate. But we don't have to pass it only the coordinate we're providing. We could also do something here like some, say, cosine of I time to that coordinate. And we can see what that would look like. Cool. So basically, it's moving the xy position of each coordinate over time. So we get this kind of bouncing effect over the square. Cool. So that's going to give us the ability to kind of play with these as we go over time. I think moving things is the simplest operation, but we can also do things like shrink or expand them. So if instead of adding this, let's see, what could we do? We could multiply it. What does that look like? Cool. So that's going to look like growing or shrinking this as we go. So remember, we're kind of multiplying a scalar here by a vector. So we do get a broadcasting effect where both the x and the y axes are moving simultaneously. If we wanted to just shrink or expand just the y or the x axis, we could also do that directly. But to do that, we're going to have to make a vec2. So let's do that explicitly. So we'll say vec2 f32, and we'll multiply by that. So this x value will go between 0 and 1. That gets multiplied by our current position, and this will go in the same. So this will expand in one of the two axes. Oh, did I do that wrong? I think that's right. Maybe I didn't save. 1 second. Okay, there we go. That looks better. So we're just expanding the x value. So I think this is a little confusing. I want to kind of look at this a little bit in our pictures before we kind of dive in further of what is happening here. So what we're saying is that here is our screen, and we're running our function at each pixel on that screen, right? So at first, what we did was we simply ran an indicator function that checked whether we were in this box. So that gave us the basic square, where you kind of just look into that box and see if you're on or you're off. But what we're doing now is, for each of these, instead of just looking at their position, we're instead looking at a position where we multiply their x value by a smaller value, right? So that shrinks them along this axis, which means they end up being inside the square. Well, this one doesn't, right? And so that's why it looks like it's expanding, because these ones are turning on because we're multiplying where they check on their value itself. And if we had been multiplying them downward, we'd get that same effect. So this is slightly backwards than how we normally work with these systems of values. Now, we can keep on applying this technique where we basically change where we look. So let's say this is our orig, and this is where we look. So that is the value here, look, and then this is our color. So we'll call this our transformation. Cool. And I think what we want to do is we want to kind of consider what all the transformations we could actually do to these shapes in order to get a new shape as we go. So what are the transformations we might want to apply here? So we might want to say we want to scale them. We might want to translate. We might want to rotate, etc. And all of these are going to basically be some sort of transformation of the original. So we'll call this the transformation we apply. Cool. And the transformation we're starting with was just this scale transformation. And the scale transformation we said was you'll multiply it basically by the inverse of how much you'd like to stretch it or grow it. So if we did like 0.2 and 0.8, we would basically transform it by that value. So this one is basically stretched by 5 times, and it's grown by about 20%. Cool. So within here, we can basically apply any affine transformation that we might want on this shape. And we can do this by, again, just applying math. So we want basically representations of scales, translations, or rotations. The way this is commonly done is by making a matrix that we can then apply to the original value we got here. This is something that LLM will be able to easily do for us, but let's make it a little kind of easier to learn by kind of creating a couple of these ourselves. So let's ask Claude, say, can you create scale affine transformation matrix for us? It should take the x and y scale and return a 3 by 3 matrix. Cool. So the matrix we're going to get is going to look very similar to the one that we just looked at. So Sx, Sy, and then this final value 1 here. Generally, we can ignore this bottom one for now and just think about this as being a diagonal matrix that multiplies at the scale on the x-axis and the y-axis by our value. So let's accept that code. And let's create that here. So we'll say scale matrix. We'll say, what did we do before? 0.2 and 0.5, or 0.8. Cool. So this gives us this matrix transformation of our square. And interestingly, the times operator also works for matrix multiplication in these shader languages. So this went from being a vector-vector multiply to a matrix vector. Now, the only thing different is that this orig value is a vec2. So we need to somehow change it so that it's a vec3, so we can do that matrix multiply. Cool. So we have this vec32 equals this value here. But now we're going to redefine it. Let's call this orig2. And our orig will be a vec3, f32. And we can create that vec3, f32, simply by taking orig2 and then adding or concatenating a 1.0 to the end. So now we have this vec3 with those positions here. So we're passing this around, and then this orig transformation on our value gives us that. And then we will simply take the xy at this point here. Okay, so we did all that work basically to get back the same value we had before. Let's actually make this the inverse of these, because then we can write it in a more standard form, where this is, say, scale this by 1.2, and let's say we scale this by cosine of I time as we go. So we'll say, like, I don't know, 0.1 plus that. Cool. So now we can actually draw this transformation, and it will change over time like this. Awesome. Cool. So we don't have to have this just be red the whole time. Let's make the color a little bit more interesting. So let's say, I don't know, why not just keep it up like that? We'll just toss in a cosine there, and all the colors will get a little crazier. Awesome. Cool. So that's our scale matrix, but we can basically represent all the other affine transformations with matrices of a similar form. So let's ask ChatGPT, or sorry, Claude, I should give them credit to draw our others. So can you make a rotation, let's say reverse rotation matrix? It should take the radians as input. Cool. So we get a matrix that looks quite similar. This top part here is going to represent the actual rotation, and the rest of this basically is the same as scale. It basically keeps that in its position as it goes. So we can now make that be the transformation we're interested in. So we call that, let's say, reverse rotation. What was it again? Matrix. Should give it shorter names. Let's say 0.5. And that should give us our transformation back. So now we should have a square on its side. Great. And the other colors change as they go. We can also make this turn over time. So we'll do the same thing we did before. We'll say cosine I time. So that's going to change between 0 and 1 as we go, or sorry, yeah, let's start with that. It's going to kind of turn and then turn back. Cool. And because these are matrices, we can also multiply them. So let's call this T1 and this one T2. And we can apply both transformations on our values. So T1 and T2, this is a matrix multiply of a 3 by 3 by a 3 by 3, then by our vec3 value. This produces our final vec3, which I'll type here. Okay, so now we have a spinning, scaling rectangle. That looks pretty cool. It's amazing how quickly these things run in practice. You kind of just type it and you get some cool diagram out. Great. Well, let's finish things off. So the last kind of matrix we would want to produce is a transposition matrix. Transposition is going to actually utilize the last row or the last column of this matrix. So can you produce the transposition matrix? It should be reversed. Oh, that's, sorry, I meant to say translation. Cool. So this one is going to allow us to translate over time. Over our location. Over its arguments again, it took in just these two values. We could also have passed a vec2. Let's say it's 0.5, 0.5 to start with. And then we'll just apply only that matrix to our output. Cool. So yeah, that makes sense. We moved it up and to the right in our coordinate system. Yeah. So now we can try applying all of these. So we'll move it up, and then the rest will be applied as we go. Cool. So in this case here, we are, let's see, let's get the ordering right. So if we were to apply the T3 here, oh yeah, everything's transposed in terms of the way I normally think about it. So if we apply this T3 last, you're going to basically, the rotation is going to be centered here, and the value will start there. So it spins in this direction. So the kind of order of the multiplies matter. Because we're applying the transformation to our kind of pixel coordinate as opposed to the square directly, it's going to be kind of slightly reversed to how you would have done this in, say, SVG or something of that form. And so we're able to kind of produce that output as we go. Cool. So now we have the ability to kind of create these arbitrary shapes. We're able to transform them in arbitrary ways and basically produce our outputs of that form. Let's add a couple more shapes, and then we can dive into some other more complex topics. So yeah, what shape should we do now? I guess probably a circle. So circle seems like a reasonable one to start with. Cool. We'll let Claude tell us how to do this. Cool. So it's using a function called length. It's probably pretty clear what that is, but let's ask and just get a sense. Cool. So it's going to give the magnitude. It looks like it works for any vector length. So it could be vector 2, 3, or 4. In our case, it's a vector 2, but it's able to produce that output. So let's then run this with, instead of a square, we want a circle. So cool. So let's start with the circle itself, just so we can see what's going on here. So instead of look like this, let's just set look equal to orig. So in this case here, we just have a basic circle. The color is changing from the other parts of our setup, but we just have a basic unit circle, and the rest of the transformations happening on top of that. The reason we get kind of ellipse shapes is because we get ellipse for free by having the scaling operations on circles. So by kind of scaling them in a uniform way, we get kind of the ellipse output. Great. So that gives us, let's say, the red color. We can include both of these simultaneously. So let's say we have a C1 that will be our red color, and let's have this be C2. Let's C2 equals, let's say orig for our square. In between, we can do kind of any arbitrary operations we want. We could kind of mix those two to get our final output. Here, we're just kind of rendering them on top of each other as we go. Great. So in general, this method for drawing, the kind of fancier version of this goes under the name of a signed distance function. We're using basically just an indicator version of this in 2D, but we can have all sorts of variants of this as we go. Let's add some other kind of properties into our setup. I think another one would be just the idea of a line. I do know offhand how to write this, but I think it'll be more interesting if we just go through the AI to get a sense of what this function looks like. So we say, how do you produce a signed distance function for a line segment? So we're going to take in basically A and B are the two positions we're interested in, and P is the actual point that we're passing. And it's going to give us the final value out here in the setting of this form. And then it's going to give us some code. We can kind of look through the code ourselves to get started, although we're getting into this realm where everything gets a little bit complex and very short. So I think it will be helpful to actually read through their explanation. Let's copy this code in, though, to get started with. So we have a line segment. Let's just call it line segment to get started with. So P is our point. A, B are the ends. Cool. So let's draw this out in a picture. So there's the line, and we're interested in whether our point is kind of on the line or whether it's off. So this will be basically 1 in our setting, and this will be 0. So we have to actually calculate that value. So we're going to get some intermediate line segments to get started with. So P minus A is basically that point there, and A minus B is basically that as we go. And the key step in this formula seems to be the dot product between this vector and this vector. So basically where this would fall onto that line itself. And then we're going to basically calculate the value, the length of that. So let's look at their explanation. So P minus A gives you that point, and B minus A gives you that point. We're going to take the dot product between them, and then we are going to call this clamp function. So let's see what that means. So clamp ensures that the projection stays within the line segment here, and this is our length, is our final value. So PABA times H. Oh, well, let's try it out and see what it looks like in practice. Hopefully it didn't lie to us. So let's comment this all out for now. We'll call line segment on our orig2 point, and then we'll make our A and B be vec32 of 1.0, 1.0, and vec32. Let's say minus 1.0, minus 1.0. And then we'll just have the red value. The others will be 0 for now. Cool. Okay, so we have our line segment here. The sign distance function is basically telling us how far we are from that line. So, well, let's turn off the color change for now. Makes it a little confusing. Cool. So we are basically 1 when we're on this line, and as we get further away, we will basically still have a positive value based on how far we are until we get to basically 0 and go off the line entirely. We can make this a little sharper by saying we only want it to show any value when it's relatively positive. So to do that, we're going to use this step function. So if we say step, and we give it the cutoff of, let's say, 0.75. Let's see what that looks like. We get a very thick line. Let's make it lower. Oop. Maybe, wait, step, let's see. Let me make sure I have the arguments to step right. I have them. So wait, let's see. If this was 9.9, what would this be? Weird. Oh, is it? Maybe it's negative. So let's see. It definitely gets more, gets less red. So C, I see. So we want to say like step negative C 0. Huh. Okay. This is the thing that is a little bit annoying about this whole process, is that you can't really debug or do any printing in this setup. I guess we can reason through what this would look like in practice, but maybe let's read the code more. That's probably a better way of doing it. So the final thing is basically going to be the length to, okay, this function will return the shortest distance from the point. Okay, not a true sign distance, as always returns a positive value. So if the distance is small, it should be on. Cool. So let's say C is less than 0.05. Is there a negative step? How do you go the other way? Okay, let's add this for now. This is an embarrassing function to have in your code base. I'm sure there's a trivial way to do this. But let's say less than step 0.05 C. Okay, cool. Now we have our thin line. And we can go even smaller here. Awesome. Great. Okay, let's rotate this line, and then we can move on to something slightly different. So to rotate it, we're going to apply the same trick we did before, where we make a transformation that changes over time, and we're going to apply that transformation to a ridge. So we'll say T2 times a ridge, and then we're going to take just the xy of that. Awesome. Cool. So what can we do with this? I think maybe one thing that would be fun to do is to make something like a clock. We can basically use the line and the fact that we have a circle to kind of draw that in practice. So the plan would be to basically use AI to try to get it to talk us through how we would basically take the code we have and draw something like this that rotates around in a circle in that way. So we'll basically draw this going upwards and then have it basically do the calculations, the trigonometry, to basically rotate this for us. Cool. So I think we have most of what we need for that in practice. Let's play through it though. So can you use these functions to draw a clock in black on a white background with a red hand that rotates around each position using I time? Okay, so this is a little bit more complex than I was thinking. It does define, let's see, the clock radius and the hand length. That looks good. Clock face. It's going to draw the arrow marks. Okay, we don't need that for now. Let's start with this to begin with. Let's remove the hour marks. I see. So it's going to change, it does the calculation basically and then draws the line segment. So it doesn't know that we have rotation, but it does have the other aspects. Okay. And it didn't return anything. Can you return the final color? Okay, let's give it a try. See how well it did. Oh no, hour mark. So we killed that. Okay, so we have our clock. We don't have the hand. So why don't we have the hand? So the clock hand was here. That gets added with clock face. Okay, let's just have it do hand color for now. Let's see where it is. Okay, cool. So there's the hand going around. That got added in. So that's going to be in the red channel. The cloud hand, oh, I see the, I guess the white would be everything. Okay, so we need the final value to be, let's see, I think we want something like to mix the clock and hand color. Okay, well, let's see. Clock. Okay, let's try this part one more time. I think they got mixed up down here. Can you combine the clock hand in the red channel with the clock face in the, let's say, green channel? Cool. Okay, so we have our clock. It's going the wrong direction, but we do have that in our final output. So that's pretty neat. Let's see. I think the last thing I wanted to do was, no, I don't know. I think we can declare success there. It is going the opposite direction. Let's change the angle, and then we can call it this part a day. So I think we want the hand angle this direction. Great. And we can make it maybe a little bit faster. So let's do I times 5. Awesome. Cool. Okay, great. So we now have the ability to make shapes. We can make circles, we can make squares. Similarly, you could make polygons or other things in this output. I think the next thing I thought would be fun to do would be to try doing things that require multiple steps. So one of the things I think is pretty neat on Shader Toy is when people make kind of diagrams with multiple particles kind of bouncing off of each other, or things like cellular automata where they kind of bounce around. That stuff is really fun to do with GPUs because you have a lot of things running simultaneously. The only problem with this is that if we have something like a cellular automata, we need the ability to maintain state. So that's going to be a bit harder to do with a single shader. Shader Toy has this ability to do multiple steps in its output. And so we can take advantage of that to try to create some of these kind of fancier outputs. Let's create a new project and put that together, and we'll talk through what that looks like in practice. So I played a little bit with this before, but let's start from scratch. So I'm going to make a new directory called automata, and I'm going to copy in our Python code, which describes the shader Troy itself. We'll call that automata2. And then, well, let's start from scratch with our output. So we're going to have two steps for our automata. So we're going to have automata a.wsl and automata b. So to do this, let's look at our kind of template. So I think I have it here. So basically, the only difference in our code is we're going to have this thing called a buffer. And the buffer is going to, well, we'll talk through as we write the code, but let me get it all set up first. So we're going to have two files, automata1 and automata2. And this first file is going to handle the movement of the automata. And the second will handle the drawing. And this part here is going to be the movement code. And this part here will be the drawing code. And then we just say shader.show. Cool. And to start with, let's copy our simple shader. So we have this shader main function. And we'll put that in automata B. And automata A. So to start with, we'll have automata A kind of not do anything. It'll just kind of pass stuff through. It'll be a blank. I guess we do need to return something. So let's say we return vec 4, f32, 0, 0, etc. But then automata B is going to be the one that actually draws stuff. So for now, let's just have it draw a red color. Okay, let's just make sure that runs before we start coding. Shader channel buffer is not defined. Okay, I think we need to import all that stuff. Buffer render pass object has no texture. Did we ask for texture? Give me one sec. Sorry, I see I have a question. I don't know if I'll make a blog about this. I think it's similar to some of the stuff I've blogged about in the past, but mostly just learning for my own sake. I thought it would be fun to basically make interesting kind of videos with this as we go. Cool. Let's see. Let me make sure I didn't break anything. So it says, let's go and look at our error. Buffer render pass object has no attribute texture. We asked for a texture. Hopefully this is not on their side, but I could be wrong. Let's check and make sure it looks the same as my starter code. Shader show. Okay. Shader main, that looks right. For a channel repeat. Cool. So sorry, what we're doing now is just checking. So this one ran fine. Okay, cool. This is what we're trying to build. Our current version is missing an argument. Okay, maybe it just requires some more fiddling with the actual code itself. The shader looks good. Shader toy, B, buffer A. Okay, well, let's talk through it and build it out, and then we'll see if we can fix this error as we go. The big difference with this setting is that we now have this first pass, which is going to be a shader called automata A. In that shader, we're going to handle the actual movement of the automata. And the output of that is then going to be the input of this second step here. We're going to be able to basically access that value in order to draw the output that we would like. To do that, we're going to need to run in our first step basically the generation of the data that we want the second step to utilize. The name of that is going to be iChannel. So whatever the output of this first stage, it will go into basically an iChannel 0 that the second stage can access. This will give us the ability to kind of basically use state of our system. Now, in order to use that state, we first have to initialize it. We're going to initialize it into basically the red channel of our output. So we're going to have an if statement in this first part that basically says if we are at frame 0, so that's the first frame that we generate, then we are going to basically initialize where we're at. So we want to do that by basically putting a random value into this first position. Otherwise, we are, for now, going to basically just return whatever the value was in iChannel. So we have to basically first ask how we can actually access that channel. So how do you get the value of a channel in WGSL? Oops, sorry, I should be a little bit more specific. So this channel, this iChannel thing is actually called a texture in WGSL. So this is a texture 2D. It's basically like a 2D matrix that has a bunch of values in it, and we'd like to pull a value out of it. So there's a bunch of these called sampling. The one we actually want to use is called texture load. So texture load is basically going to just pull out the specific value that we're interested in. So just to give you a sense of what we're doing, so this is our buffer. This is our first stage. It basically outputs I channel 0. And this is our second stage image. And it's basically going to output to the screen. And this gets in basically the last I channel 0, and this one gets in that. So this here is called a texture 2D, and that's both basically given to our shader, but also outputted from our shader. So we need to access it with this texture load here. So we're going to say texture load I channel 0, and we're going to load from our current position. So that's frag coord. And I think the last argument is always 0. So current value. And we're going to set that. We're basically going to get the red value from that and set the red value to that for now. Cool. And now this value has to be a random value to start with. So random 0, 1 val. And I don't know how to get random values from WGSL, so we'll let it do it for us. Okay. Takes X, Y, and Z. I wonder why it takes X, Y, and Z. How is it using those? I guess it's taking our coordinates. Say, can you do this from X, Y, vec2? So I guess it can't really make random values, so it's just kind of hashing our current X, Y coordinates in order to do that. So if we pass in, I guess that's good enough for now. So if we pass in our coordinates, we should be able to get out that value. So binary random from x, y. I guess in practice you just pass in noise, kind of like jacks or something, to get out random values. Great. So this basically says if we're initializing, set it to a binary random value based on the current xy coordinates. Otherwise, load that value in and then pass it to the next stage. So we'll do that for now. And then on the next stage, automata B, we're going to do the same thing. So let current state equals texture load. And we're going to load from our frag chord, our frag chord from I channel 0 and value 0. And then we'll just set red to our current state and then 1.0. And hopefully this runs. I don't know why we got a bug earlier. It might have been just something silly, hopefully. Otherwise, we can debug some more. Okay. Different error. Image coordinate does not. Okay, so we got. Oh, and just to talk a little bit more what's going on here. So Naga, this is a compiler for WebGSL, for WGSL, actually written in Rust. So this is a Rust-specific kind of compiler for this language. I think it's a different one than actually used in the browser, but it's still interesting. So the error we're getting is image coordinate of type does not match dimension. So we gave it f2 I channel 0 does not match dimension. Expression 3 is invalid. Oh, I see. Okay. I think the problem is that we're passing in float 32, whereas it looks like texture load takes in an int 32. So let's try casting that. We haven't tried that yet. So I think I can do vec. I think I can do this to cast it over. So I think that should work and get us to our original position. Okay, different error. Composing 4 components. Current. Okay, this is on the other one. So automata B. So current state. Oh, so I loaded in the full value, but I'm only using the red value. So let's say we only load in red. Okay, getting close. No definition for identifier XY. Binary random. Oh, so this is the LLM code failing on us. So we passed in XY, it passed in XY. No definition in scope. Oh, no, it was us. So frag chord to the random value. Okay, great. We're getting there. So this is our noise. So this is our basically random Bernoulli noise. Each of the red dots is where we decided a kind of original point was, and each of the black dots is where one was not. Cool. Let's make this bigger and also less likely to be turned on, just to get started with. So this is in, okay, so we want to make it bigger. So we're going to turn the resolution here. Equals, what did we do before? It was 800 by 800. And the automata, we want it to be less likely to be on. So let's say step has to be greater than 0.8. Okay, so only 20% chance they turn on. Resolution. What did I do? Buffer, render pass. Oh. Oops. Oh, sorry. I think I deleted something by accident. Okay, great. So here's our full output. These are random, although I guess they're not. I can't tell. They look slightly off. I guess maybe that's the hashing we're actually seeing in practice. Okay, that's fine to get started with. So we have our full setup. It's going to run buffer 1 and then buffer 2. Buffer 1 on the first stage actually creates the points in the automata, and then the second stage draws them for us. The reason we're doing it this way is because we don't have the ability to basically maintain state any other way. So we actually have to change where the cellular automata points are after the first stage. So let's think about some ways to do this. I think maybe the first one we'll start with is to just do kind of a old-fashioned automata. So we'll do, I guess, we can ask the LLM to do basically any of them for us that we want. I guess the most famous one is the kind of Conway one where we sum up the neighbors and we basically determine our value based on what the neighbors' values are. So cool. So Let's see what they did to implement it. So this is counting neighbors. So it's basically just going to go around in a loop. If it's at our position, it does nothing. Otherwise, it basically gets a neighbor position. It loads the texture at that neighbor, and then it sums up the ones that are live. So that's the first stage. One thing to note is that it's using var here instead of let. When we do let, it kind of defines a constant value. When it does var, that value can be mutable. So we're seeing here it basically summing up over live neighbors to get the value. And then here are the Conway rules. So the rules are if more than half are, if our value is positive and there are less than 2 live neighbors or more than 3, then we die. If we're dead and there are exactly 3 live neighbors, then we become alive, and then that's our current value. Cool. So let's run that guy and see what happens. Oops. Okay. It got one of these wrong. Oh, again, it's me. So I shouldn't make this current value. I should make this new val. Cool. We get a pretty fun output. Again, it's amazing how efficient this is. I mean, we only wrote like, I don't know, probably like 30 lines of code, or like let the language model do it. And we get a pretty fast system in the output. Cool. Let me answer some questions while we have them, and then we can play around with some more kind of these particle systems. So there's question is, are you using TensorFlow? No, so just to remind everyone what we're up to, let's just do a quick review while this plays in the background. We are using a combination of different technologies, but all of them are based around WebGPU. So WebGPU is this developing standard to run GPU code from the web. There's a whole specification of what it actually does in practice. What we're doing is we're using a library called WGPU. WGPU is a Rust library that implements the WebGPU standard, including its own kind of compiler. And we're using basically Python bindings to this called WGPU Pi. WGPU Pi is another complex and interesting system that lets you do all kinds of cool stuff on WebGPU. The particular way we're doing it, which makes it much simpler, is that we're using a front end to WGPU Pi called Shader Toy, or an implementation called WGPU Shader Toy. Shader Toy basically is based on this website where people produce all these really cool graphical programs just by writing these kind of shaders. What's novel, I mean, this website's been around for many years, and it's has extremely amazing examples. How did we get to the full set of examples? Yeah, so you can do like all kind of crazy stuff like this in these shaders. What I think is exciting about what's going on now is that it's getting to a point where you can basically just write these sort of shaders and run them on the web and have them, I don't know, do lots of amazing things. How does this relate to TensorFlow? We're using the part of WebGPU that is called a fragment shader that actually draws these images. There's another part of WebGPU that specifies what are called compute shaders. And compute shaders are what people are using in libraries like TensorFlow.js to actually run neural networks online. Compute shaders are a bit more powerful in that they can utilize shared memory and all sorts of other kind of phenomena. I think we'll eventually talk about them. What's fun about these kind of fragment shaders is that they're extremely simple. You can't really do anything like shared memory. We're really just kind of fully trying to parallelize through complex things. Cool. Okay, cool. You know about this already. Okay, awesome. Yeah, I wasn't really part of this world, so I'm kind of learning this as I go. Cool. Okay, so right, so here's one thing we just built. I think this is really neat. We built it pretty quickly. There are probably other automata that might be fun to do. I think there's one that's like falling sand. I've seen this a lot. Maybe we can get them to explain it to us. Okay, so just like this, they're going to be empty or contain a particle. Particle types. Oh, okay, we'll get to types eventually. Basic rules. Gravity. Particles tend to fall downwards. Stacking. Particles stop when they hit another. Spreading may spread horizontally. Okay? Okay, this makes sense. Cool. Let's ask it to draw this one. Cool. Okay, so its implementation here is going to basically use an array to tell us the locations. So 0, 1, minus 1, 1. Okay, great. So those are the three values. I think this should be var. I think we're getting an error if it's let. Okay. New value equals current value. Okay, check if current cell is sand. Go through the neighboring cells. So this neighboring below cells. Cool. I think this should work. I get a little worried about whether this is allowed. I think it's fine. Okay. Check if we're in dimensions. So this is a new function. Let's look it up. I see. So this is going to tell us the size of input channel 0. So it gives us its xy. Let's pull this out of the loop. Great, okay. And then this is the load we saw earlier. So this is loading neighbor position to get its red channel value. If the neighbor is empty, we move the sand. So that means we go away, and then we break. Cool. Wow, so it's very it's a very language model thing to do to implement half of what we need. So it looks like it implemented the sand falling, but not the sand arriving. So we need, I guess we need two loops, one that's going to look above and one that's going to look below. So let's have it just rewrite everything for us and try one more time. Okay. Actually, I guess we probably should have given it its old code and told it to fix it. But I don't know. Looking at more of this code will help us learn the language a bit more, so it's not the end of the world. Okay, so this time it didn't use an array. that worries me. So how does it know what's above? Oh, I see. It just looked one above. We won't want that either. So we want it to fall in all directions, but okay. Yeah, interesting. Okay, so let's maybe have it write down the rules first, and then we can play through the automata. We can also look up some famous ones of these, but I think I like having the language model do it. Okay, this is a falling sand automata. If there is nothing below you, fall down. If there is something above you, take that value. If there is something below you, go down right or down left. If both spaces are full, stay where. Okay, this looks close. Let's give this a try. Does it mean to comment this? Probably not. Oh, we forgot here. Oh, shoot. So these all have to be... I wonder if we can redefine frag chord. Probably not. Let's see what happens. Oh, wait. Yeah, that should be fine. It is redoing them. So wait, what was the error? Maybe, can it not do this? Does it have to be 0.1? Let below. This expression has type F32. Oh yeah, I guess you have to individually redefine them all. Blah. Okay. Make a variable fc that is vec2 i32 first, and then use that one. It's still amazing to me that it just gets those little things right. I know it's like pretty obvious, but it's still very fun. Okay, if below. Okay, what's the error here? Expression 45 is very less cannot work. Okay, so now we have a problem where the dimension, I see. The problem is that this needs to be a vec I32. So it kind of knows the language, but it doesn't know the type system yet. So it kind of keeps on screwing up the type system. Okay, oh, the sand moved, but it moved very quickly. So we probably need to slow it down a little bit. Oh, it kind of just went up to the top right away. Okay, let's try a slow it down. So maybe we only move every 30 frames or something. So if iframe mod 30 equals 0, then we do this. Otherwise, we do what's it called? Current value. Huh. Okay, we did something wrong, but it does look pretty. Yeah, so there's a question in the chat about quaternions. Yeah, quaternions are a really interesting world. Quaternions relate to what we were doing in the beginning part of the talk, where we were talking about rotations. But at least everything we've talked about today, it's all been 2D. So we're just doing 2D shaders and 2D signed distance fields. So we can do everything with basically just basic matrices. I'm not sure quaternions give us any benefit there, at least to start with. But none of this really plays in automata world. For automata world, I think we just need to make sure we are loading the right values and moving things around in the correct way. So I think the biggest problem is that we don't know what's up and down. So let's switch up and down so we go the right direction. Oops. So let's try that. Huh. Okay, so things are definitely disappearing, but they're not moving. So what do we want? We want if... Okay, so what's this saying? So this is saying if we're at the bottom... Okay, if we're, okay, so below is, okay, so if we're greater than 0 and the loaded value is equal to 0, then we're 0. Okay, that means we drop down 1. That's good. If above y is less than tdim y, and the above value is greater than 0, then we get the above value. Okay, that's good. That means it fell on us. Okay, let's try that for now and just see what that does to start with. So this should just be everything falling. Not totally sure why it just disappears. Shouldn't it just drop down 1? What am I missing? If... So that's below. This is above. We're ignoring these for now. These are our frag coordinates. Okay. So it looks good. Yeah, I kind of was expecting it just to fall down slowly. The fact that it kind of disappears means maybe I don't totally understand something. So I think we should be able to load at that coordinate and get its red value here. Seems right to me. So let's see what's actually happening. Maybe it's just happening too quickly. So the red values are... They are kind of just disappearing over time. Okay, let's do one more debugging pass, and then we can call it a day. Thanks everyone for sticking around and learning about this topic with me. I think it's plausible there's something we misunderstood about texture load, but I think it makes sense. So we start random, we get the current I channel frag coordinate R value. That's going to be 1 if it's on, 0 otherwise. Then we set new value equal to cur value to start with. And then we get our texture dimensions. So it's possible that's the part that's off. I wonder what happens if we just don't check for that. If we go out of bounds, what would happen? I wonder if it will crash or not. Let's see. Um, oh, I see. I guess what's happening is, I see. We have to check both of these cases. So, okay. I guess this is the issue with still relying on language models at this point. So let BV equals, okay, so this is our below value, and this is our above value. Okay, so we're only equal to 0 if BV is greater, BV equals 0 and AV does not equal 0, else if AV does not equal 0. Okay, let's try that. Return value sum does not match the function return value. What do we return? Oh, we need to return vec4 f32. Cool. Okay, so we have more falling. Oh, but it says stop. Huh. Okay. Below value has nothing. Above value is not equal to 1. Then we become 1. Okay. Cool. Awesome. Okay, let's turn up the speed now. So we have, okay, so let's render every, I don't know, 5 frames. Cool. Okay, let's make it a little bit less red. So that means our first random part, we said what? It was 0.8. Let's make it 0.2. Oh, that's all red. Okay, we want it to be 0.99. Oh, we don't have the bottom. Let's add a bottom. So what is it? It's frag fc dot y is greater than 0. Cool. Okay, now it's kind of snowing. So I guess the last thing we need to do is we need to make them roll off to the side. Let's make it a little bit more snowy. So we had 9.9. Let's make it 9.6. Make it a little bit faster. What did I say? Oh, actually, I guess we don't even need this anymore now that it kind of works. Oh, okay, cool. So those are like stacking up where there's a lot in that row, but we need them to kind of roll off to the side. Cool. So now we just want to check if the side fits or not. So we're doing the below left part. So if, okay, so what's the logic here? So if the below is greater than 0, okay, so if their below is 0, then it's that, okay. Or, so let's get all these values. So let's have it be left value, right value, below left, below right, okay, so then the check here is, it's whether, I guess the check here is a little bit more complex. So we have to check whether the one at our top right or top left has a value. So let's have it name all of these. Add variables for top right, for above right, and above left. Cool. And then make this condition check if a particle fell from our top left or top right. That's not exactly right, right? We want it to check whether given the automata above, check whether anything fell from our top left. Oh, I see it. I see it. I guess we also need our left and our right values. All this work. Okay. Add left and right values to. I guess the only problem with this is it's going to merge particles, but for now we'll just. They fall here if their under value is taken already. Cool, okay. That'll be something. Let's see. Oh, wow. Okay. Oh, cool. So stuff's like falling off the edge and falling down. Oh, that's pretty cool. Right. I guess we need to default if both are there. It picks one, but still pretty cool. So I guess the sand. Awesome. Okay. Well, let's see. So I think we're basically at 2 hours. So I think we can call this a success and end it there. This is not the kind of perfect way to do this, but I think we're relatively close. I think we have to default left or right, or maybe fall in a random order. But still, it is neat that it runs so quickly, and it's actually not that much code. So I guess let's just summarize what we did, because it was a lot for 2 hours. So we're basically playing around with shader toy style methods. We want to basically understand what the heck this code is doing, how people are able to draw such wild things with such little actual code under the hood. These are going to get a lot crazier in that they're going to, like, I don't know, be like all like this and out there. But I think a lot of the code that you see in these is going to be quite similar to what we did. If we look at this code here, we can now understand what a rotation matrix is. We can understand that this is like the palette and these are colors going on. And then we can understand maybe what's actually going on in drawing them. We were doing it not with the standard OpenGL framework, but we were doing it with WebGPU. In particular, we were using this WebGPU Pi setup. There's a lot more here. So I think there's a lot of other things we could play with. We didn't even touch on 3D at all. We only did kind of fragment shaders where we were trying to draw the individual pixel values and their given colors. In practice, that's all Shader Toy lets you do. But if you look at some of the examples here, you'll see a bunch more 3D kind of things. Let's go to WebGPU. Let's see, WGPU examples. You'll see like a lot of like crazier stuff going on. So these are the full examples. They also have, I think, some demos that you can play with. Yeah, I think these are cooler. So like a lot of these basically were exactly with the kind of stuff that we've done so far. So let's see. Oh, actually, maybe this is not running on my computer. But if your computer's set up, you can see a bunch of these examples. We didn't even get to kind of cubes or 3Ds, but we can try that in kind of future sessions. And so we drew two things today. The first was this simple example where we kind of played with shapes. And then the second was this automata example where we played with multi-stage rendering. So yeah, those were all the things that we built in the last 2 hours. Cool. So thanks so much for tuning in. And yeah, hopefully we can do one of these again soon.